Hello and welcome to the third part of this QED lecture, Hypothesis Test 1, where we're now going to look at the what I call the concept of the universal tester. So before getting into the detail of how you work out probabilities using, for example, a t-test, we'll look at a universal idea that applies to all kinds of tests and apply that to the three RCT examples we've discussed before. So the three examples, if you remember from the previous week, there was the idea of cooking oil vouchers and marriage age. So as an incentive, young girls are given cooking oil vouchers if they don't marry under 18 years old. And there's the village schools, so they built village schools in the treatment group of villages to see if that improves student learning, because they didn't have to travel so far, particularly the girl students in Afghanistan. And the commitment accounts in Malawi for the tobacco farmers, when not only did tobacco farmers get given accounts to keep money in, but it was a special account where once they put money in, they weren't allowed to take it out until the following season. And they examined the effect that would have on their ability to save and invest. So any test at all that you use to analyse the results of these randomised control tests is going to follow this common pattern. And I think of this common pattern, I call it the universal tester. So, for example, we'll go through these one by one. In this example here, the treatment group for this experiment get vouchers for cooking oil as long as they remain unmarried. The control group, on the other hand, they don't get vouchers, whatever happens. And after 10 years, you record what was the age of these girls when they first married. And you find this. So in the control group, it was 19.47 years. The treatment group, it was almost an extra year, 20.20 years. How can you interpret that? Well, a test will help you decide between these two possibilities. It could be that, okay, the mean first marriage age in the treatment group was indeed higher than the control group. So what it can't do is it can't test for measurement error. In other words, that the girls were not telling the truth about being married, or when they got married, or they forgot. So it can't tell you those measurement things. But it can tell you the chance that that happened through random. It wasn't caused by the voucher scheme. Some other thing caused it. For example, the girls in the treatment group, maybe a higher caste, more educated, better, or more religious, or for whatever reason they decided they were going to get married later on because of some other characteristics. And we have to assume that selecting those girls having those other characteristics which made them get married later is not something systematic about our scheme. We didn't just deliberately choose the treatment group from the well-connected families, for example. We have to assume we took a really completely random sample, so there's no bias in the sampling, but just by chance we happened to get girls who had these other characteristics which meant that they then got married later, and it wasn't to do with the voucher scheme. So just random allocation of those other characteristics meant the treatment group got married later. So did that happen by chance? Or if that didn't happen by chance, then the only thing that could have caused those girls to get married later was the voucher scheme. So what the test is going to help us decide, did by chance we happen to pick girls who married later because of some other unknown characteristics, or was it the voucher scheme that did it? Let's get to the next slide. So this is the basis of all statistics tests you will ever meet. In any statistics test, you have got some theory about the world, and you've also got some evidence, some data. And the idea is that you believe something about the world and you observe the data. And if the data fits in well with your theory, so okay, if I expect this to happen, then yeah, I see that, that's not be surprising. Then you quite happily go along with the theory about the world. So if you think that it's the daytime, you walk around, you see people sunbathing, or you see people doing their washing or shopping, and you think, okay, that fits the pattern. But if you start thinking something which is very unlikely, like you think it's the daytime, and then suddenly you see that people are pulling their curtains, and you see that there's bats flying around, and you think, oh, well, it could be just that there's some bats out there early today. And then it starts getting dark, you think, oh, perhaps there's an eclipse of the sun, and then it gets completely pitch black for hours, you think, oh, perhaps the sun's been swallowed by a giant ghost in space. At some point, you start to think, actually, perhaps my theory that it's daytime may not be true. So this is the idea of all statistics tests. You hold on to your theory until you see something which is, if your theory is true, it's very unlikely. So what you need is some way of telling how unlikely your theory is, which is whether the test, how unlikely the observation is, which is where the tester comes in. So the tester tells you, if your theory is true, what's the chance of seeing that thing? And when the chance of seeing that thing becomes very, very small, you think either your eyes are tricking you or it's time that your theory got jettisoned. So let's put some more concrete stuff on this. Oh, there's the, if the assumed theory makes your observation too unlikely, reject the theory. So here we get some more concrete stuff. What you started with here is, I assume that the vouchers made no difference to marriage age, which means that what happened must have been caused by some other characteristics. So I assume that the vouchers made no difference, and I observed that there was this difference in the treatment group of 0.7 years, at least 0.72 years. So what I want to know is, if I'm correct that the vouchers made no difference, what's the chance of randomly selecting these two groups of girls and happening to find that one group has got characteristics which mean they get married at least this much later, their ages that much later when they get married? And the probability you can work out is about 0.15 or so. I think I've got the exact figure here. 0.14, so about 15%. So if it's true the vouchers made no difference, the chance of seeing a difference in the evidence as big as that is about 15%. So what should I conclude? That's this chance here. So here's my choice. I can either believe that indeed the vouchers made no difference, and a gap with a 15% chance roughly of happening came up randomly, or I've got to conclude that the vouchers did cause the girls to marry later. So did the vouchers cause the girls to marry later? So pause the video here and have a think and say what you would plump for, and I'll say what I would probably go for in a second. So I hope you pause the video for a moment there. I think 15% is not that unlikely. It could well come up. 15% is a reasonably high probability. It wouldn't be that shocking if it happened. So it could well be that this was a random thing and the vouchers didn't have an effect. Or on the other hand, it could be the vouchers did. So the problem with this sort of result is the evidence is consistent with both outcomes. It's certainly not so unlikely that I'm going to throw away my idea. So and in this sense, there's no correct answer for this, except you definitely can't put it up here. So I would probably put it around I'm not sure what happened here. F you can definitely rule out, A you can definitely rule out, B pretty much you can rule out. So it's going to be either C or D, so it's around 50% maybe, or you're just not sure, because that could easily have been a random result. So it's quite inconclusive. Okay, let's go on and see another example. This is the Afghan village schools example. So you can read about this one on the JPAL websites. Really interesting one because it's obviously a high cost one because they're building schools in villages. But I think they did it with the pipeline. And so the other villages got schools later. So anyway, the first phase, the treatment village gets schools and the control group don't. Oh, it's until later, I'll put that there. And then you do literacy assessments before and after. And what do you find? Well, you find that the slide won't advance. But they won't advance now. So there was an increase. The control group went up by 6.3%. Great. The treatment group went up by 12%, even greater. So here's your universal tester. You start with the assumption, okay, I assume that the village schools made no difference to literacy schools. They're going up anyway. So the village schools made no difference. If I assume that, the chance that randomly you could see, because of the characteristics in the girls that happen to go and to live in each village, that randomly they could increase by this many percentage points more if the village schools had no effect. So it's just down to random selection of other factors. The chance of that happening is, off the scale, it's 0.026, which is 0.26%. So like less than 1/4%. So less than 2 times less than 3 times in 1,000. So incredibly unlikely to happen. So you've got a choice here through believing. Either you can carry on believing that schools made no difference, and this gap came up, which has got a 0.26% chance of happening, just happened to come up randomly, even though the schools made no difference. Or you have to conclude that the schools did have some sort of role in making that happen. So what would we go for there? Again, pause it. Okay, so in this case, I would definitely be saying greater than 50% and probably greater than 95%. It's going to be one of these. It definitely has greatly strengthened the likelihood that the schools had an effect on pushing that that rise in literacy. So I will probably go for B, possibly C, but probably B. Unfortunately, you can never go for A. You can never be completely sure, but you're in this sort of territory up at the top end here. So it's definitely provided quite strong evidence that the schools had a causal effect on literacy, because it's so unlikely that that would have happened randomly. Okay, so the final example is the Malawi tobacco grower savings, where the treatment group get these commitment savings accounts, control group villages don't. There was another group who got the savings account without commitment, but we won't discuss those. We'll just look at the treatment group that got the treatment group that got the commitment savings account compared with the control group, and they looked at how much they saved up before the next harvest, and this is what they found. So before the next harvest, the control group had saved up 21,812 kwacha and the treatment group 23,658 kwacha. Here's the familiar universal testing scheme. The idea I have in my head is that commitment accounts didn't really affect savings. That's my idea. What's the chance, if that's true, that just randomly we just happen to select the two treatment groups so that these people, because of unknown characteristics, randomly got allocated to the group with the commitment savings? They would anyway have saved this much higher because of other things not to do with the savings account themselves. So what's the chance of that happening randomly? And it's about 35%, 33, 34%. So you can either believe that the commitment accounts had no effect and something with a 34% chance of happening came up randomly, or if that's too unlikely for you, you have to believe that commitment accounts did cause savings to increase. So again, please think about this. Pause for a moment. Okay, and so here I'd definitely be saying in the not sure department, because there's no strong evidence there at all. Unfortunately, you can never really conclude these things, that when you have this this negative result that it could easily have happened per chance, it doesn't mean it doesn't show that it wasn't caused. It just shows you can't rule out the randomness. So you cannot, all you can say is not sure. And so all these definitely ruled out, but not sure. So when it could be 50-50, but I think not sure is the best answer. So you can, it's the results like the ones for the schools, when it comes out as very unlikely what to reject your idea, then you're pretty confident you can put it up here somewhere. When it could have happened randomly, then you're not sure where it is. It's got a non-result in a sense. Okay, so what have we got? This is the basis of all statistics tests then. So if what you're thinking makes the observation too unlikely, reject it. If it doesn't make it too unlikely, then you don't know whether to reject or not. It just hasn't really told you very much. It just says that the theory could well be true, but it still could not be true. So if an assumed theory makes your observation too unlikely, reject it. And now we need to look at how you get this number on the dial to work out how unlikely it is. That's what's called the p-value of tests. That's the chance of seeing the observation if the assumed theory is true. And the smaller the p-value, the more confidently you can reject the assumed theory. So once this gets really, really small, then you know that if your theory is true, it's so unlikely what you're seeing that the theory, that means that the theory, there must be something dubious about the theory. So the smaller the p-value is, the more confidently you can reject the assumed theory. And in conventional terms, when it's below 5%, we say we reject that with 95% confidence. If it's below 1%, we say reject it with 99% confidence. Sometimes instead of 95% confidence, you say at the 5% significance level, or this one's at the 1% significance level. So conventionally, you might look at 5% and 1%. But generally speaking, it's just the smaller the p-value is, the more confidently you say that the assumed theory you started with can be rejected. And if the p-value is big, then really this result, you can't be sure whether it's rejected or not. Okay, so now it's time to work out exactly what those p-values are. And the first test we look at is the example for t-test, because from now on, you get into the details of how you work out those p-values. It differs from test to test. So we start with one called the t-test. The others, like the test of correlations, chi-squared test and others, have different techniques for working out the p-value. So we're going to start with a simple t-test, see how you get to a p-value from that in the next section. But for now, thank you for watching.